This topic is called Medieval Laws of Falling, which is kind of an interesting title. I've called it that because I'm going to try to tie some specific formulas that, from the perspective of this course, these are kind of like two special case formulas, you could say, because where we're headed towards is an overall group of formulas that kind of comprise what is called kinematics, in other words, the study of constant acceleration. These are two kind of like special cases of those, but you can tie both of them to some important historical discoveries. One of them, this one here, the first formula there, the notation. So one of the other reasons I'm doing this is I want to share with everyone some new notation here. That is stated as V bar. We're not going to use that like a ton, so if you're worried about memorizing lots of notation, maybe don't stress too much, but we may see it again in the future, and I'll probably talk about it again just to make sure we all know what I'm saying. Physics in that sense is a language. I don't necessarily expect everyone to master all the notation right away, and I also don't want people to be scared of it really, because we do use a lot of subscripts and we do all these like little things to variables. Some of it's kind of similar to what you see in math classes. Some of it is uniquely physics, so you might see things like this in math. But when you see a symbol in this class with like a horizontal line over it, that is not like an arrow, because if it were an arrow, that generally means it's a vector. But this means average and is pronounced V bar, or whatever. If it's a different symbol, it would be something bar. And again, it's usually the time average of that thing is equal to 1/2 final. So if F stands for final, we've seen that before. And it turns out this was already kind of known in the 14th century. So we'll see a little bit of that come up in the examples. The second formula there, this is actually Galileo's law of falling bodies expressed in more modern notation. D is equal to 1/2 gt squared. And we'll see also that this is a special case. You can derive either of these from the overall set of kinematic formulas. And this is actually, the second one here is kind of a special case of the first, maybe most important, I don't know, kinematic formula. So that's something we'll see. But Galileo basically discovered these mathematical patterns. And one cool reason that I feel compelled to kind of look a little bit in history is to have us all gain kind of an appreciation of how long it took and how many different people it took to discover all the different components that now comprise kind of the body of knowledge of physics as is taught in a course like this one. Because for many of us, this is a very difficult course. I acknowledge that. And the symbols can seem strange, and and it's taken a long time for them to become what they are now and to be used the way that they are now. And so it's a lot for us to get used to them. We often have to do that in a very short time. But when we recognize how much knowledge we're really getting from over the centuries and many, many people's life's work, it makes us appreciate why we have to kind of put a little effort into figuring out how to use these tools and how to think about them and how to apply them to problem situations.